Hi, I'm Josh Wiedemeyer, and today I'll be presenting PyLingual, a Python decompilation framework for evolving Python versions. I'm going into my third year as a McDermott Fellow at the University of Texas at Dallas, and if you'll forgive me for a second to shamelessly bat my eyes at recruiters, a lot of our team is students that are graduating in the upcoming spring, so find us after in the wrap rooms if you're interested in opportunities like that. Ooh, let me get this back. Am I in the right thing? Perfect. OK. So how many of you guys use Python? A good number of you, and for good reason. Python is the most popular programming language in the world, making up nearly 30% of programming tutorial searches as of last month. And lots of, let me get this actually working, if I can. There we go. Lots of Python programmers means lots of Python malware. So from baby's first Discord scam to sophisticated threat vectors, Python malware samples are popping up more and more these days. Here's one. It's just a simple dropper. It disables some local defenses, downloads some code from the internet, and runs it. The details aren't too important, but we're going to use its simpler functions to illustrate Python decompilation techniques. Let's start by zooming out to the code object hierarchy. In Python bytecode, every single class, function, comprehension, and so on is a code object. By looking at where these code objects are defined, you get a tree, the code object hierarchy. Fortunately, all this structure is given to us for free by CPython. So we get to live in a nicer world than the Rust folks this morning. Also importantly, code objects can be considered independently when decompiling. Let's zoom in on the extract zip function, since it's the simplest function here. It only has 2 lines of code, so we're going to walk through it manually to build some intuition and fluency. As we get started, 2 things to keep in mind. The Python interpreter is a stack machine, and it's helpful to decompile statement fragments and put them together as you go. So the first thing we see is we're loading a global zip file symbol and the capital zip file method. Then we're loading another zip file attribute. Why do they keep naming these things the same thing? It's their problem, not mine. And we get a string, R, and we're going to call a method off the top of the stack. Putting that together, and this is starting to look like Python. The next thing we see is this setup with opcode, which unsurprisingly is related to with blocks. We'll get to the real implementation later, so put a pin in that. And that's our first statement decompiled. That's our first statement. We'll go through the next one a little bit faster. We start by loading the zipref.extractAll, a standalone extract2 value, and a quick function call. And that gets all wrapped up in a nested function call. It's going a little bit quickly, and the rest of this bytecode is all implicit. That's to implement the cleanup logic for the with statement we saw earlier. So now we have completed the decompiling of one simple Python function. In just 10 slides, we've decompiled 2 lines of Python code. So if you'll bear with me for the next 500 slides, we are going to walk through the rest of this simple dropper malware. Unfortunately, the timer that the production crew is showing me says we don't have time for that. So let's use a decompiler. Uncompile 6 and decompile 3 are the most well-known and well-respected names in Python bytecode decompilation. But unfortunately, they don't support Python 3.10 yet. Rocky's working on it, and he's always looking for helpful hands. So if you're interested in contributing, go ahead and give him a shout. PyCDC is another Python decompiler that aims to support every Python version. But here, the coverage of language features suffers, and it doesn't know all the opcodes. So we're still left unable to decompile our simple dropper malware. So what's the problem? We just did this with our hands. It can't be that hard. Python bytecode changes a lot. Every version, just the opcodes, the instructions available, not even talking about code generation changes or new language features. Those opcodes are changing every version. Historically, it's been about 10% of the specification that's changing, but especially in the past couple of years, we've seen dramatic changes to the bytecode specification, which has really hindered the scalability of Python decompilers. And not only are those versions changing the Python bytecode dramatically, they're coming out every year. So it's really hard to keep up. Maybe if you can afford a full-time Python reverse engineer, and if you can, come find me after. I'll give you a business card. But anyway, faced with this problem, I did what any scrapping young programmer does. I sat down, rolled up my sleeves, and asked ChatGPT. And surprisingly, that looks exactly like the code that we just decompiled. And if you read through it, it is the exact same. It's correct in this case. So are we done? Can we just throw all the decompilation jobs to ChatGPT? Unfortunately, no. We're not quite there yet. On this toy example and most code that doesn't fit on a slide, generic large language models start making significant mistakes. They're not built for this, but they're trying their best. But just because AI is not a silver bullet doesn't mean there's nothing here. Language models are really good at pattern recognition and filling in the gaps. They're flexible. Decompiler programs are great at consistent data transformations at scale. They're rigid and they're precise. Combining these ideas, we can make an all-terrain decompiler that naturally adapts to superficial or surface-level changes in the bytecode specification. And so I introduced PyLingual, a neural decompilation framework for Python bytecode that breaks the decompilation task into 3 components: bytecode segmentation, statement translation, and control flow reconstruction. Let's start with segmentation. Simplification is the name of the game. We want to cut up the bytecode into chunks that correspond roughly with source-level statements. The best way for us to learn that association is to let the compiler tell us. The line number table is a debug symbol that many of you may be familiar with. It's used for localizing exceptions. So if you've ever seen error on line 23, the line number table is where that's coming from. So unfortunately, lines aren't statements. You can have multiple statements on one line, or more commonly, your linter probably does this for you. You can have one line or one statement spread across multiple lines if you have a large dictionary or a large function call. And also, in the wild, the line number table could be arbitrarily manipulated, so we can't trust it. In a controlled environment, though, statements can be lines. Using some syntax tree transformations, we can put every single statement on its own line and get a consistent and reliable mapping between bytecode instructions and source code statements. Using that association, we can build a data set to train a small language model to predict these statement boundaries. BERT is an older architecture that's been around for a while. It's only about 110 million parameters. Compare that to 1, 2, 3 billion parameters for the small end of large language models these days. But it's helpful for us. So now that we have these statement-level chunks, we can translate them into source code. To do this, we're going to borrow, out of the box, techniques from natural language processing, since translation has been studied there as a core problem for many years. And there's a lot of subtasks that are shared between code translation and natural language translation. You have simple translation, where words are directly translated one for one. Proper nouns, or in our case, strings, variable names, and so on, can be reordered, copied, moved around. And you can also have semantics that are implied purely from context. Taking advantage of these capabilities and using the bytecode, source code data set that we produced earlier, we can simply train a statement translation model out of the box to translate Python bytecode. Unfortunately, the performance is never great out of the box, so we play some tricks. I can't go into full detail of all of these things right now, but the details are available in the white paper. We normalize the bytecode to hide some distracting details and reduce the variance that we show to the models. We try several candidate segmentations to see if we can find one that works. And we also include a statement corrector model to spend additional compute on harder problems. Now that we have that flat list of source code statements and their association with the bytecode, we can piece together a complete Python program. So from this flat list, we're trying to get here. Flat list, right here. The first thing to do in this process is to understand the control flow in the bytecode. We're going to ignore all of the non-control flow instructions here. Coming up to the setup with, it's going to prepare an exception handler block, which will continue until we see this pop block instruction. And as long as there's no exceptions, we can continue on to the end of the function and return. When there is an exception, we have to perform the manual with cleanup. And depending on the return value of that dunder exit, which implements the with cleanup, we'll either re-raise the exception or continue to the end of the function. And this return value is actually duplicated because it's a short enough code segment, and the function exits immediately anyway. So when we're trying to reconstruct those control scopes, the important question to ask is who decides when each node executes? Starting from the bottom, the re-raise and the return value are decided by the return value of the with cleanup. It's either going to go and re-raise the exception, or it's going to go to return value. The rest of these blocks are actually decided by the setup with, because that's the node that's preparing the exception handler that could cause them not to execute. Now, let's play a little bit of dress up. I'm going to change the shape of this graph, but it's going to still be the same graph, I promise. And we're going to annotate each node with the source code that is associated with that node. And this is starting to look a lot more like what we saw originally. And you'll notice that some of these nodes are even implicit with no source code directly associated with them. The important thing to note here is that when nothing crazy is going on, the indentation level of the source code is pretty tightly coupled with the depth in the control dependence graph. So we can see at level 1, we have the with header, and at level 2, we have the with body. Reconstructing that control flow, and we get that one indentation level. So all that for this. It's helpful, and it gets us to where we're going. So to summarize, we've segmented the bytecode into statement-level chunks, translated each of those statements one by one into source code, and then stitched together those source code statements to form a complete Python program. Now, equipped with a flexible Python decompiler, we're ready for the rest of the example. And so I'll give a quick demo of the web service. So currently, PyLingual is available freely as a public web service at pylingual.io, and we're committed to open sourcing by the end of the year. So keep tabs on that. We'll get back to you. We detect the version of the Python bytecode by using the magic number at the start of the file, load the appropriate models, process it, send it through the pipeline that we just discussed, and now we have some Python source code. Perfect. Hooray, automation. So we've now fully decompiled this file, but we're still left with one big question. Does it work? The more skeptical people among you might be doubtful of the use of language models and statistical approximation in decompilers. And rightly so. You shouldn't trust the outputs of language models. So we need to verify the outputs of the decompiler, not just in our lab, not just for our evaluation for the papers, but for you, for your files. We could do manual verification, but unfortunately that's labor-intensive, error-prone. It doesn't scale. I can't go and look through every single file that someone wants to decompile. Eventually, I will grow old and die. And if you could look through the bytecode and manually verify it efficiently, why do you need a decompiler? Another popular method of verifying decompiler outputs is equivalence modulo inputs. Basically, running the original program and the decompiled program with the same inputs and making sure that you get the same outputs. There are some limitations here. One, it's expensive to run. It requires me to actually run the code that you guys are uploading, and I'm ready to host a decompiler service, but I'm not ready to host remote code execution as a service yet. And the equivalence guarantees that you get are limited to the inputs that you test in the environment that you test them. So you get weak guarantees, it's expensive, it's not what we're looking for. So let's shoot for the moon. Let's shoot for perfect decompilation. It's an old idea that's gone by many names: exact decompilation, absolute decompilation, byte-wise equivalence. The main idea is that a decompiler undoes a compiler's work. So a compiler should be able to redo it and get the same result. So we recompile the decompiled source code and compare it with the original instruction by instruction, and making sure we have an exact match. Using this perfect decompilation metric, we can finally verify that we did decompile the original code correctly. And also using that perfect decompilation metric, we are able to evaluate the PyLingual decompiler alongside the existing decompilers on a sample of 3,000 random files from the Python package index. It's where you go when you pip install anything. We see that PyLingual is able to consistently provide best-in-class performance across versions 3.6 through 3.12, which is the versions that we cover right now, but to put a little bit of context on these numbers, uncompile 6 still has great historical version coverage, going all the way back to Python 1.0. So if you have one of those older Python bytecode samples, please use uncompile 6. But none of these decompilers are at 100% accuracy. Even the best decompilers are barely cresting 80. So what happens when they fail? Since we are testing each instruction one by one, we can identify exactly where the disagreements start. And we can use that to localize decompilation errors to a small region of bytecode and even independent lines of source code. In this case, there's only one line that's wrong. Looking at the bytecode diff, we can play a little game, spot the difference, and see what actually changed. Why was this line decompiled incorrectly? And the only difference here is this binary subscript instruction that got moved up into a different part of the statement. At the source level, that just means that the slicing was done in the wrong order. We can patch that at the source level by hand as an end user and run the same perfect decompilation test. So recompiling again, checking the instructions one by one, getting another piece of feedback. If it's still wrong, we'll get another localized error message, and we can keep going. Or if it's right, we can get a success message. Hooray. We get a solid done state, which supports a feedback loop with end users to turn almost correct decompilation into fully correct decompilation. For future directions, we're looking at applying graph learning techniques to the control flow reconstruction, since control flow is still the major source of manual effort in scaling our decompiler. We're also looking at incorporating large language models into that patching feedback loop we just discussed, because following the success of guess and check architectures like alpha code and alpha geometry, as long as we have a strict mechanical verifier, we can throw language models at the problem and make a little bit of progress and reduce some of the workload for you. And lastly, we are setting our sights on other languages with properties similar to Python, because so much of our pipeline is already driven by data. We have our sights set on Lua for now. If you're a Python product owner, you might be feeling a little bit nervous. We've already had a couple of instances where high-profile products written in Python have been uploaded to our service for decompilation. So I wanted to call attention to a couple of obfuscation tools that you can use to help protect yourself. PyArmor is a bytecode-level obfuscation tool that partially compiles your Python code to C and applies some other fancy techniques. It's freemium, so its basic features are available, but it requires a license for its best stuff. And then Oxyrai is a source code-level obfuscator that scrubs all your variable names. It's free. It doesn't stop decompilers, but it makes the decompiled source code much harder to use. None of these are going to stop a dedicated expert, but they will make it a pain in the ass to get through your code. So the key takeaways are that for PyLingual is the best available Python decompiler for Python versions 3.6 and above. For older Python versions, uncompile 6 is still great. Perfect decompilation provides case-by-case correctness guarantees and supports post-hoc error correction. And finally, bytecode obfuscation tools are currently effective against automatic Python decompilers. Please deploy responsibly. I've got a lot of extra time here, so we have plenty of time to sit back, relax, have Q&A. So I guess the floor is open for questions.
Hi. Is your tool open source?
It is not currently open source. It is available as a free web service, but we are committed to open sourcing by the end of the year. So keep tabs on that.
Thank you.
Of course, follow-ups are welcome.
I wondered if you were looking at classifying patterns in code using your framework in some way to maybe find definitions of behavior in code patterns you see, maybe?
Could you rephrase the question, please?
Your frameworks allows for a wide range of code patterns to come up, right?
Yeah, you can upload any bytecode, although it's primarily for is primarily for code that's been compiled with the CPython compiler, which is the dominant Python compiler.
I think that my question's direction is can there be maybe a functionality of security measurement for code that is inputted into your framework?
It's always possible to run that study. We do collect the PYC files to support future research. We don't have that analysis capability right now, but if there is a metric that comes up that helps us quantify the security worth or security value of each of those bytecode samples, then that's certainly a study that we'd be happy to run.
Okay, thank you.
How are you dealing with heavily obfuscated binaries?
Let's see. We've received a few obfuscated binaries. I think most of the obfuscation tools are still very effective against the Python decompilation tools. And as far as I know, the options for Python de-obfuscators are fairly limited. That is something that's going to be open for future work. And maybe the PyArmor devs will have to watch out.
All right, thank you.
Hi, I have a question regarding PyInstaller. So if a source code goes through a PyInstaller method, which kind of compiles the Python code into an exe or a binary, is there a way that PyLingual can reverse decompile that? Have you?
I'm sorry, could you repeat the question a little bit louder, please?
Sorry, have you used PyInstaller? So
Python server?
Oh,
PyInstaller. Yeah, so what PyInstaller does is it packages the PYC bytecode in with the interpreter to make a standalone executable. Right. PyLingual's place in the pipeline is after using a tool like PyInstExtractor or PyUninstaller to get the PYC bytecode out, and then you use PyLingual to ultimately recover the source code.
Got it. Thank you.
Hi. I like your methodology. I think it's very clever. Do you think the similar methodology also works for other languages, like those static type languages?
Let's see. I think the main challenges you might face when expanding or extending this methodology to lower level languages is going to be how comprehensive the compiler optimizations are. One of the core steps that you would need to look at is the segmentation step, where we cut up the bytecode into statement level chunks. If you have a higher level of optimization, like you might see in a C compiler, maybe that level of segmentation would no longer be valid, and you would have to use larger units of segmentation. The other roadblock you might run into, especially if you're going into languages that compile down into machine code or x86 assembly, is that for the perfect decompilation test, you need to know the compiler that was used to produce the original input binary. That is easy information to get in Python, where almost everybody uses the CPython compiler. But that may be more challenging if identifying the compiler and its configuration is itself challenging.
OK, thank you.
Hi. Have you used your tool against large collections of malware written in Python or other collections of representative, interesting pieces of Python code to look at?
Let's see. So we haven't done independent investigations into Python malware repositories, but the tool is open. So we have received people uploading Python malware, and we do some of that. If you have a particular set of Python malware that you're interested in reverse engineering, we'd be happy to help. Even if the tool is giving you some problems, our lines are always open.
Is the service also open as an API or just an upload?
It's currently primarily through the web service, but you could make calls to the API directly. We don't have any special key safeguards on that. It's open. It's public. Okay. So you're welcome to use it. And again, I'll reiterate that we're planning to open source it by the end of the year.
Okay, great. Thanks.
All right. Seeing no questions, it sounds like we're good to take an extra 5 minutes to kick back and relax. Thank you so much, and enjoy your black hat.